You can check, it's changed. It should be Friday. Huh?
Submitting on paper or to you?
Well, what you're gonna do is upload it, your code and everything up there. Then in class, bring it in with the signature. Just a printed thing, because I need that form. I don't have to have it, but I'm supposed to have it, so, if, they're concerned about plagiarism and problems, and I've heard this, and they're very suspicious of things out there on the internet and stuff like this. So I'm just making sure it's your work. Try to do a good job on this one. It's not that hard if you think about it. You've got an object flying. You know the position of the object at all times. You have a radar that's rotating. So the key thing to get this right is find an equation for R, the radial distance between the actual object and the antenna. It's pretty straightforward to do this. It really is. And then when you do this, remember what your power return to that radar is really just going to be transmitted power times gain of transmitter, gain of receiver, which varies with time. That's the key. Varies with time because it's revolving. Then it's over 4 pi cubed R to the 4th. Once you have R down, it's pretty much straightforward, but you do have to do the plot. And by the way, you don't have to make a movie. To just make sure if I run it, I can see it, okay? Because I did this thing, I spent some time with that movie, and movies can be very, if you do the uncompressed stuff, it was like 500 megabytes. So, and this is an old, all right. Anything else before we go? Yeah.
I already made my report, and I just assumed Lambda was one.
Lambda is one?
Yeah.
If you've already done it? If you want to, sure. Okay. I mean, I'll give you that, because that's not really a big deal. All right? It's a ratio of power received over power transmitted that I care about. And, go ahead.
I did my report already too. Is it okay if we digitally sign the signature in that? Or do you want us to break it?
Just print it and sign it.
Okay.
I need this, not for my good, but for somebody else up there that wants this stuff, and, they go through them, and there's a long story behind this, but I need this for ABIT too, the accreditation agency, so I have to make sure this is done. And your report doesn't have to be that long, but just, describe what you've done, how you did it, why you did it, and then the results. Because what you're gonna see is there's a tremendous amount of power difference from the time the plane starts to the time it's right overhead. It goes zoom, like orders and orders of magnitude. So, anyway, anything else? How many of you took a shot at the project already? All right, good. Now, I'm warning you, this is important you turn it in, because I don't think you can pass without this, but I might be wrong. It's not that hard, but you do have to take a shot at and really do a good job. As far as other things with that, if you've got other questions about how to do something, you can come to me or ask your friends, but try to make this project your own work. That's what I'm really looking for. And when you did it, did you use MATLAB or Octave? MATLAB. Octave's free, it'll work too. The only problem with Octave is the graphics aren't quite as nice as MATLAB, and it's a little slower. That's the only thing. I use Octave all the time now, because my MATLAB licenses sometimes don't work. All right, so today, in this last week, the last thing we're gonna cover are filters. And these are I'm not gonna cover Butterworth, just Chevy-Chef filters. How many have had Chevy-Chef filters or Butterworth, anybody? You have? Where'd you get them? What class? Digital signal processor? Where'd you get them?
Yes.
Are you in it right now? Who's teaching that? Okay, because these filters are based on table values that you use for the normalization. But in fairness, I just want to say this. If you have your books, actually, if you have your books, the table I'm going to be referencing, it's table 10.3. This is an older book, but if you take a look at it, it's going to have a whole bunch of values for Chevy-Chef filter coefficients. Anybody have your book up? Can you see where that table is? You have your book. An older book. What page is that on? On page 583. So these are called Chevy-Chef filters. There are Butterworth filters that are a little better in terms of how sharp you can get the corners, But these are chip filters, and they're actually, this stuff's used all the time. And the reason I'm doing this is because for microwave engineering, a lot of times you want this type of filter for a lot of different reasons. So what it always comes down to is, I knew this was gonna happen. Now that is a brand new marker. When you have a filter, it comes down to this. You're starting with some voltage source, and you're gonna have either a resistance or a conductance right here. And then, depending on the type of filter, there's two types, and I wanna make sure I do all this what he does. This would be type, this is gonna be, I'll call it the A filter system. And there you're gonna have some G1 here. This is called G0. It's always equal to 1. Then there's going to be an inductor here, and that's G2. And then there will be something G3. These are low pass to start, but they'll transform into high pass and even band pass. And then you're going to have something out here, G of N plus 1. And this is the low. And so, now to go through this, if you look in this book, first thing is, this is a low-pass filter. This is one design. The B design, where the parallel version only, where these elements switch. We're going to have the voltage source here, plus or minus Vs, some value of G naught equal to 1, and then you're going to have a series inductance here, G1, a capacitance here, and that's going to be G2, and a series inductance here, G3, but these two will almost always be the same as far as I know. And then this goes to the load here, which is G of N plus 1. So the first question you might have is, what is N? N has to do with the number of filter elements. So N is just the number of filter elements. That's it. So for this one, there's 3 elements that are part of the filter. It's right here. That's the load, and that is the source. Now, they're all normalized. This is going to come, you'll understand this in a second. And if you have your book and you look at that table, you understand it, or hopefully you'll understand. So, first thing is, G1, what is it? Well, G1 is a resistance in this figure, and it's a conductance in this figure. That's the only difference. So, remember, resistance and conductance are inversely related. Y'all follow me on this class? Just bear with me, you'll see it. Then the second thing is, G1 is an inductance for the series inductors, or it's a capacitance for the shunt capacitors here and here. Gn plus 1 is the load resistance, and don't worry about that right now. And or the load conductance, so it's resistance up here, right there, and the conductance here. Until you see this actually take place, what we do, there's a lot of questions you have. If you read Wentworth's book, he answers the questions by showing you examples. More or less the questions you have, he'll answer. So here's the steps, and this is laid out in your book. The first thing you do is determine the corner frequency. Now, when I say corner frequency, that would be the 3 dB frequency. If you have a low-pass filter, you want it to start acting like a low-pass filter for some frequency above which the thing starts dying off at 20 dB, 40 dB, or whatever. Y'all with me on that? If it's a high-pass filter, it's the point where all of a sudden the high-pass filter kicks in and allows the signal to come through. But it's called the corner frequency. So the thing you do is determine the corner frequency. Alright, and then you have to determine the number of elements you want. And that's N. After that, You go to and select the values of table 10.3. I think it's 10.3 in your book, isn't it, that table? Or is it 10.4? So 10.3. So you select the values from 10.3 and you transform the values with regard to impedance. So if you're in this design, G naught is, or there's going to be some G naught equals Z naught, which is the characteristic impedance. If it's this design, G naught is going to be the characteristic admittance. Then there's some transforms. I'm going to put these up here, and then I want to work some examples, because a lot of this stuff is kind of mumbo jumbo. You know, they don't do a proof on how these tables were developed and stuff like this. When you had your digital signal processing or digital image processing, did he go through and show you how these things were found, these values? All right, I want to tell you, Butterworth and Chebyshev values are basically found from, they're determined from a big, it's a mathematical formula. Are you familiar with Chebyshev polynomials at all? You know? Well, don't worry about it. They're basically coefficients of these Chebyshev polynomials that came out of probably a whole lot of work before computers were available. Right? So, anyway, getting back down to this. So then, G naught is going to be equal to Z naught or R naught, and those are just the impedances. By the way, this is from microwave engineering, so typically this load is 50 ohms and this source is 50 ohms. That's just typical. These are what these filters are geared to. They can be geared to a lot of other things, but right here, his discussion in the book is about that. Then, obviously, since I just said that, Gn plus 1 is equal to Z naught as well, or R naught, so it's a characteristic of the impedance. Then, now this is an intermediate stage, it's not the final stage. We're going to find these values that will be used for the next step. You're going to get something called L prime, which is equal to L times R naught. Here, I'll explain this in a second. L comes from these G values over there, which is G1, and I'll get to that. And you'll get C prime equals C over R naught. And then finally you get the final values, and these are the ones you care about. You're going to get L double prime equal to L prime over omega C, and you get C double prime equal to C prime over omega C. And omega C is just 2 pi times the corner frequency, whatever that is. It's the frequency you want the filter to start acting as a filter, or the beginnings. So now I'm going to go through, this is very terse right now. And there's not a lot of mathematical explanation for why this works. It does work, but remember this. We don't have a whole lot of time to go through all the mathematics. And I don't think I've ever done that in a lower level class. That Chebyshev polynomials and things like that we use at the doctoral level courses to master sometimes. So now I'm going to go through an example, now that I said all that. And let me erase that. And we're just going to go through, this is in his book, I think it's in his book at least. When I was in graduate school, I had a course in passive filter design, and it used KIE1 and KIE2 series for a lot of this stuff. Now, in Woodward's, he doesn't mention any of this stuff, but all these things are based on series expansions of a lot of the stuff that come from, that are KIE1, KIE2 series, that you don't need to know about, but you have to appreciate one thing. Filter design in itself is an entire science. There's tons of stuff for passive and active filters out there. And now with digital signal processing, almost all the filtering is done in the digital domain. This is an analog filter, but these are still used. That's the reason I'm doing this. Okay, so here's an example. Design a first order, so it's going to be a first order filter. It's a low pass filter with low pass. And he wants 3 dB of ripple. I'll explain what ripple is in a second, but you probably can guess. And he wants the cutoff frequency for this to be 1 gigahertz. And he wants, the characteristic impedance of this is 50 ohms. So it's 50 ohm source, 50 ohm load. First order means one element. When they say order, it's the value n, so it's just one element, which is nice. And this is, all these filters start from a basis of a low-pass filter design, then they're transformed to either high-pass or band-pass. Try to appreciate there's a lot of stuff here that goes unexplained in his text, and it's generally something that is much higher level than we want to talk about. But this works, and you will be using these filters, I think, for some of your, they do analog filters still, right? And you've had your microelectronics, don't they? Right? They still use them. All right, so, and I know they use it for microwave all the time. So for this one, if you look at the table now, in his book, how many have your books here? I'm just going to show you. If you look at this table, there's 3 sets of values for these G values. One, the top one is for 0.1 dB of ripple, which is very small ripple. The second one is 1 dB of ripple, and the third is 3 dB of ripple. That would be on the insertion loss graph. So now, what is ripple? Well, he shows you, and I'm not sure exactly what this is. This is on page, well, I'm sorry, it would be figure 1031, I think, in the book. Take a look. 1031, it just shows a figure. Here's what it really is. This is for a high pass, but it could be a low pass filter. So if this is your cutoff frequency, omega C, and you're talking about the insertion loss here in dB, then what will happen is there'll be some kind of a ripple like this before it starts coming up as a filter. This would be a high pass filter. With me on this, class? The amount of ripple is that. If there's 1 dB of ripple, it would go like that. If it was 3 dB, it would be more, basically less fidelity. It's not as good a filter. If it was something like, they wouldn't have anything more than 3 dB, but when they get down to 0.1 dB, it's just about undetectable if you look at that. Now you should be able to see that in this graph you have your book. You see that? On page 96. Right there. He's just showing you the different levels of ripple. That's for a high pass. It would be the same for a low pass or a band pass. It has to do with just the amount of really overshoot, undershoot that happens there. And it really isn't that big of a deal, but there's never going to be a filter with more than 3 dB of ripple that would be allowed. Usually you want less than that, and he even has the good ones that are 0.1 dB. Then if you look in there, the next thing he wants. So he gives these values, 3 dB of ripple, 1 gigahertz, 50 ohms, and now you have to go in that table, if you work with me on this one, if you can look at, if you have your books, you can see that for 3 dB of ripple, that's the bottom one. And since there's only one element, there's 2 values that you have to get. For G1, it's 1.9953, and G2 is 1. So, when you take a look at this, this filter is going to be about as easy as it gets. But this is the source voltage. This is 50 ohms. And now this is going to be a capacitor. The value is second, and it comes over to 50 ohms here. So the first value I had is G1 is equal to 1.995, I believe. Yeah. And G2 is 1, which just means the load's 50 ohms. The only thing we care about is this. Now, next you have to get the value of that capacitor if you want to use a capacitor for it. So for this one, you first get C prime. I'll put this here. This is an intermediate step. It's just the way it's done. I mean, we could go right to the final step, but he's showing you what's done in general. This is called normalization. So C prime is just going to be equal to this value of G1 divided by and it's gonna be, Z naught, I believe, he uses Z naught R naught, I think. Yeah, Z naught, and that comes out to be 39.9 millifarads. This is really 1.995 divided by 50, and that's 39.9 millifarads, which is extremely large. Then, from there, remember this is the intermediate step, then we get the value of C double prime, and that's going to be simply that divided by omega C. C prime over omega C. So that's going to be 39.9 millifarads divided by 2 pi. We want this at 1 gigahertz. So it's times 10 to the 9th, and that gives you a value of 6.4 picofarads. Now, if you actually, you guys use spice, right? LT spice or any of that stuff. If you actually build this circuit, put 50 ohms there, make that the capacitor, 50 ohms there, and then you did a frequency sweep, and look at the insertion loss, you're going to see you get exactly those values. 3 dB of ripple, everything, it's precise. The only thing I'm doing though is looking at values from a table. Very little true mathematics, just using tables. Next thing I'm going to do is another example. And I want to say one thing. The key is getting the values G1, G2, G3 from that table, and then realizing you have one of two designs for low pass. Either you have series inductance, parallel capacitance, series inductance, or you have this would be a low pass filter, or you're going to have parallel capacitance, series inductance, parallel capacitance. Either one will do the same job. The performance is identical. The values will change though, depending on the type. And the one we did was the simplest filter of all. So the next one, our next one is going to be, I think this is in his book, tell me if it is. It's going to be a third order filter with a cutoff frequency of 2 gigahertz and 50 ohms. I did this before I came. I was going through this stuff. I was going to do something else with the filter designs. We can do these with simulations, but I thought I'd just work through this because and try to answer any questions you have. It doesn't make a lot of sense because it's like, how do these values come about? Just have to accept the coefficients that are from these Chebyshev polynomials. All right, so next, the next one is, he wants a low-pass filter with a cutoff frequency of 2 gigahertz. So this is a low pass. And quarter frequency of 2 gigahertz. Nothing new there. Characteristic impedance equal to 50 ohms. And he's talking about, now he wants 0.1 dB of ripple. That would be in the insertion loss. That's very low. So there's more elements involved too. And it's a third order filter. So write that down. That just means the number of elements is equal to 3. That's it. Nothing significant. And by the way, we can do this with either the series inductances, 2 series inductances, 1 capacitor, or 2 capacitors, 1 inductor. The way he did it in his book for the first time is this one. So he's going to use, this is going to be 1. And this will be an inductor, but it really doesn't matter for this part actually. And then you're going to have this is 1 also. So this is G1, this is G2, and this is G3. These are just the values we're going to get next from the table. So if you look in there at 0.1, where you want a 0.1 dB of ripple, it's the bottom. Can you all see that? That's the top tube. in my figure, it's on top. Is that right in yours, guys? 0.1 dB? Okay. Now, if you look down there, third, so the number of elements, n equal 3, and you look over, you get values. And the first value you get for G1 is what? Almost 1.035, is that right? go ahead.
1.0315.
Yeah. 0315. G2,
1.1474.
Now G3 should be G1. 1.0315. You've got these values. From there, we get these intermediate values. And now, I've got this right here. So, now, we're going to get, and the equations are right there for the L prime. It's going to be L times Z naught. Let me just tell you this. When he puts that L there, he really means G. All right, it's the value you just looked up off that table. You hear me? Just make sure you see this, because when I see L, I think it's an inductance value. It's not. It's the value of G. Now this would be for the first inductance right here. So it's, this is the intermediate step. So that's 1.0315 times 50. We're going to get a value for that, and that value is 51.6, almost 50. That's L prime. Then we go ahead and get C prime. You can do it right over there, C over. But this is not C, that is the G value. You all follow me on this? But it's going to be for this element, G2. So really what I'm going to do here is, I'm just going to put G2 divided by that. It'll be the C value, C prime, because we're using this configuration. So this is going to be G2 divided by Z naught. And, or in this case, G2 was 1.1474 divided by 50. And that equals 0.023. Follow me on this? You're going to find out that G3 is the same thing as, that G3 and G1 are the same. So the values for L prime, this will be the same for the first, for G1, and for G3. How we're going to replace them. Now, that's an L, and that's a C prime. Now after that, what we have to do is get the actual values. But if you don't like it, I understand, but this is the way it's done. I would prefer a much more in-depth treatment of this, but this is how it's done. Anyway, you get L double prime, it's equal to L prime over, and then it's going to be 2 pi FC, or 2 pi times the cutoff frequency. It's L prime is 51.6 divided by 2 pi, and this is at 2 gigahertz, right? So it's divided by 2 times 10 to the 9th, and that is going to be equal to 4.1 nanohenries. And finally, the C double prime. This is the actual values that you want right here and here. C prime divided by 2 pi FC, and that's equal to 0.023 divided by 2 pi. And this is times 2 times 10 to the 9th. And that equals 1.8 picofards. I'm going to make one comment. That's a very small capacitor. They make them they'll make them small, but you got to realize that if you ever do a filter design, your lead length there can change that substantially. So you have to make sure. Usually, when you've got something like that, you want to build in something that can tune it. And I mean, like a little, very small tunable capacitor right next to it, because I'm telling you, that's a small capacitor. If you've worked around capacitors, right? Rarely do you work around 1 picofarad capacitors in laboratory work. I can't think of any time I've ever done it except with a ham radio. We took a CD radio and turned it into a ham radio for a senior project. The only time we're messing around with values that small, but that's terribly small. That's what this example works out to. So, here's the deal. This inductor right here would actually be that value, which is 4.1 nanohenries. This is going to be 4.1 nanohenries. And this value of capacitance is 1.8 picofarad, just about non-existent. So this is 1.8 picofarads. Now, if you were to simulate this thing, you'd find out exactly what they say. We would get 0.1 dB of ripple, and we have a cutoff frequency of 2 gigahertz. Now, I'm going to ask you one thing. As far as the order of roll-off, what do you think it would be for that one? For a single capacitor, do you all remember single capacitor added, the actual dB roll-off is 20 dB per decade? Do you all remember that? Well, for each one of these elements that you add, you're going to get a roll-off that goes up by 20 dB. Typically, not every single time, but this is probably going to have 60 dB of roll-off. All right, that means it's going to come down very quickly or go up very quickly, depending if it's low pass, high pass. This right here is a low pass filter, so basically the high pass stuff's going to get killed very quickly. And where it starts going down is at 2 gigahertz. All right. So that's, and again, the only thing we're doing here is finding out how to use these table values to calculate the values of the components. There's nothing in here that's in any way difficult to conceptually. You're just reading information and doing transforms. And finally, if you want a high pass filter out of this, everything starts with these low pass filter designs. What you do is the component values you're going to get are going to be for a low pass filter. When we want to go to high pass, and this is in his book, you're going to have a transform. And this is pretty straightforward, but I'll show you what it is. And high pass somewhere. High pass. Now, if you look on table 10.4, and he'll give you actually values in equation 10.73 and 10.74. The only thing we're going to do is, if we use this configuration, if we wanted high pass where the capacitors are, where the inductors are, there'll be capacitors. Where the capacitors, there will be an inductor. This is a T filter. The earlier one was called a pi filter. It had 2 parallel elements, 1 series element. So, getting back to this, if you want to do the transform, that's low pass, but if you wanted to do a high pass filter, I'll put it right here. So this is a high pass filter. What happens is C double prime will become 1 over, really, pi FC, corner frequency, times L prime. And L double prime will become 1 over 2 pi FC times C prime. Now, this value and this value were from the intermediate steps for the low pass filter. Do you all remember? Those values are actually G values, they're not G values. Those values are given by taking the values, if it's a series L, and multiplying by Z naught, or if it's a C, taking GT divided by Z naught. But this is in the book, it's spelled out. So you're going to get these values right here and do this transform. And then, if you want the high pass filter, if we're talking about using that in the high pass filter, with the same characteristics, it's going to pass everything, not break it off. Then you would have this. You have plus or minus Vs. You have your resistance here, which would be 50 ohms. Then, where that inductor was, there would be a capacitor. Where the capacitor was, there would be an inductor. And then there would be a capacitor here. And this is 50 ohms over here. And the value for that capacitor right here would be 1 over 2 pi FC L prime remember the Eltron we had was right here. And for the actual inductor, it would be, this L double prime, would be 1/2 pi FC times C prime. And this would be the same, this would be C double prime there too. And that would be a high pass filter with the same exact amount of ripple. Now, I don't expect you to go around memorizing all these equations. I'm just going to show you this, and I'll give you, if I was going to give you a question about this on a final examination, which should be in everybody's mind, then I would provide you with those tables and the actual transforming properties. I'll give you the transform formulas I showed you there. I don't expect you to memorize this stuff, just know how to use it if you need to. Right? That's what I'm asking. And the homework should provide you with all the necessary information to do this. By the way, I usually don't cover this stuff right here. Usually this is done at a higher level, and it's in microwave engineering, some of the other stuff. And there's a lot more details that are added that aren't in here, specifically how they develop these tables. And I don't have time to go through all that, but I'm going to do this. So, y'all follow me? If we start with a low-pass design, you have two possibilities. You can have either this design right here. Let me just show you this. Because we're going to do, final thing we do is band pass and band stop. I'm going to just say this. When we were talking about the beginnings, about the two types of filters that were shown, shown in your book, they're either this, they're going to be something where you either have a series inductance, parallel capacitance, series inductance. Now, when you only have one element, you only have a parallel capacitor. This is the first type of filter. This is called a T filter, by the way. Whitmer's book doesn't call it that. The other one is called a pi filter, because it looks like the symbol pi, and that's going to have a capacitor here, then it's going to have an inductors in series and a capacitor here, and the loads would connect. Capacitor, inductor, capacitor. For these things, it's always an odd number of elements. Y'all follow? You're either going to have 1, 3. The next type of filter you would have would be, if you want to take a look at a higher order filter, it would do this. I mean, it doesn't have to be on order. I said that. It doesn't have to be. It usually is. But you would just have more elements like that that would repeat themselves. Now, if you look at this and this, they're both low-pass filters, and they both, if you use those tables to get the values of L and C, remember this is G1, G2, and G3. If you use those, the actual values of G1, G2, G3 from the table, you'll get values that you have to transform using the characteristic impedance and the cutoff frequency. You'll get these values, and if you ran the performance of these two filters, they're identical, which is interesting. Because I wouldn't think that off the top of my head, but they are. They'll give you the same insertion loss at 50 ohms. There is one thing he doesn't talk about with these type of filters, and I think I mentioned it earlier. Anybody remember one problem? All right, if this impedance is very high, or you're going into like an FET transistor, something like that, with a very high impedance, then what happens is you have a resonance circuit formed there. And at resonance, you'll get very large voltages developed here and here, and it can break down this actual value, this capacitance. It can destroy it. So you have to be really familiar with these type of circuit, or these type of filters are meant for use with in microwave engineering with 50 ohm kind of loads and stuff like this. If you go to extreme values of input impedance, like just an FET input and stuff like this, then you can get all sorts of problems. You can get all sorts of resonance problems here. And just think about this. Anytime you have a series LC circuit, what if this didn't exist here? Right? What happens at resonance to this thing? Well, at resonance, if I put, let me just do this, I'm going to put a resistor R. And if I had a source value Vs, well, at resonance, these impedances cancel, right? So you're gonna get a current here, I, that's just gonna be Vs divided by R. That will be the current, right? But what's gonna be the value of the capacitor inductor voltage? Well, that voltage on this capacitor is what? That's gonna be the impedance of the capacitor, right? Which is 1 over J omega C times the value of I, right? Now, if I is large, that thing can go be enormous. It can be absolutely huge, depending on the value of C and omega, admittedly. But what you can get is an extremely high voltage here that will break it down or arc over on that inductor, one of the two. That's the only thing I'm gonna just warn you about with these things. When we teach this class, this is supposed to be an applications course, and they encourage us to tell you about problems you experience in the real world, not just the math and things to pass the course. But I'm telling you, that's one thing you've got to be careful with these kind of filters. Yeah.
Is there any perk of using a T filter over a pi filter then?
Well, Wimmer's book it shows something that I have concerns about because the same exact kind of thing, configurations are for Chebyshev filters too. I mean for Butterworth filters. But he will show you that, I'm trying to find this right here. There's a preferred one for high pass, for high impedance versus low impedance. I don't really think that's completely true. I don't even see where he has it here, but normally speaking, and like TV power supplies and all this, if you look for any type of thing that's going to take any kind of a full wave rectifier signal and turn it into DC, basically. You take it, something like this, they will have this filter. They'll use a pi filter to do that. And the real reason is the capacitor here is going right to the load, and that will be the one that more or less holds the charge, so there's not much variability, right? This kind of a filter right here with that inductor there, that's not as good as getting rid of ripple at DC. Just doesn't. This one's always preferred. So if you're ever building a power supply, you know what I'm talking about, full wave rectifier. Once you get a full wave rectified signal, now you got to get rid of that huge ripple. So the way to do it, put a capacitor there. Remember, that's going to discharge the load, so the capacitor is going to charge up. But then you need to slow down any kind of the ripple directly from here, so they put an inductor in series and have a capacitor there. That's usually the way it's done. Are you familiar with making power supplies or circuits like that? Did you have to do full wave rectifier labs at all? When you did it, you had to use, didn't you use that filter? Just a single type?
Yeah.
This is the way it's usually done, because it will make it a much more, I guess, constant signal. All right, I'll tell you what, today, I'll save the bandpass for next time. I'll go through it, but I'm going to give you some homework problems just to do, to get familiar with this. On the final exam, I will provide you the formulas. You just have to understand what they mean and how to use them, and the tables, okay? And I'll be as fair with you as I can be. I'm not liking the way I'm presenting this. I would much rather do this in a laboratory kind of environment where you actually build these things and see it on a scope or these simulations. But that's the last thing the actual band stop and band pass will be the last thing we cover next time. And the only difference is there, instead of having a single element here, you're going to have a series inductor capacitor here and a parallel inductor capacitor here. And this is in the book. That's the only thing, because then the pass band will be there. And you're familiar with Q, right? You know the Q of a circuit? Are you familiar with that? All right, it has to do, it's a quality factor. It has to do with how well or how sharp, you might say, or how narrow the band is of band pass. And we'll talk about that next time. Go ahead.
Will there be a quiz this week?
Yeah, I think what I'm going to do on Friday, this is what I'd like to do. I want to go through the review of the course. I mean, just a final exam review, because I'm going to get questions. I've been getting questions. A final exam review. Then I'll give you a quiz, and that's the one that's going to replace any missed quizzes. Okay. Now, if you didn't miss any, I'll replace your lowest quiz. So, and it's a benefit to take it. There's no downside. So, and it will be, yeah, I'll probably do it on this stuff, but I'll let you, I may give it an open book, which I almost never do, just because I don't feel like creating those tables and handing them out, so, that's about it. Remember, final thing we're gonna cover is band pass, and we can probably start the review on Wednesday. Please get your projects done, take care of those things, and, anyway, see you there. My shoulder's been killing me today, so 5 minutes.